The theory of chemical bonding is a cornerstone of chemistry, explaining how atoms interact to form molecules and compounds. Chemical bonds are the forces that hold atoms together within molecules, allowing for the formation of everything from the air we breathe to the vast array of materials we use in our daily lives. Over the centuries, scientists have developed different models and theories to explain the nature of these bonds, with the most prominent ones being ionic, covalent, and metallic bonding. These theories have evolved as our understanding of atomic structure, electron behavior, and molecular interactions has deepened. The earliest ideas about chemical bonding were based on the concept of attraction between atoms. In the 19th century, the discovery of the electron led to a major breakthrough in understanding how atoms interact. The concept of atomic structure, atoms being composed of a nucleus of protons and neutrons surrounded by orbiting electrons, set the stage for the development of modern theories of bonding. The key to understanding bonding lies in how atoms' electrons are arranged and how these electrons interact with those of other atoms. One of the most fundamental types of bonding is ionic bonding, which occurs when one atom donates an electron to another. This typically happens between elements with significantly different electronegativities, such as sodium and chlorine, Cl. In this case, sodium, with its low electronegativity, loses an electron, becoming a positively charged ion, Na2, while chlorine, with its higher electronegativity, gains the electron, becoming a negatively charged ion, Cl. The oppositely charged ions are then held together by electrostatic forces, forming a stable ionic compound, such as sodium chloride, NaCl. This type of bonding is common in salts and compounds formed between metals and nonmetals. Covalent bonding, on the other hand, when two atoms share electrons. This type of bonding typically happens between nonmetals with similar electronegativities. In a covalent bond, the shared electrons allow each atom to achieve a stable electron configuration, often resembling the nearest noble gas. The bond can be either polar or nonpolar, depending on the difference in electronegativity between the atoms. In a nonpolar covalent bond, the electrons are shared equally, as in the case of two hydrogen atoms, H2. In a polar covalent bond, the electrons are shared unequally, leading to a partial positive charge on one atom and a partial negative charge on the other. An example of a polar covalent bond is the hydrogen chloride molecule, HCl, where the chlorine atom attracts the shared electron more strongly than the hydrogen atom. Metallic bonding is another important form of chemical bonding, which occurs between metal atoms. In metallic bonds, electrons are not shared or transferred between individual atoms. Instead, the electrons form a sea of delocalized electrons that move freely throughout the metal. This electron mobility gives metals their characteristic properties, such as electrical conductivity, malleability, and ductility. The positive metal ions are held together by the attractive force of the surrounding sea of electrons, creating a stable metallic structure. This type of bonding is seen in metals like copper, iron, and gold. The development of the theory of chemical bonding also introduced the concept of molecular orbitals. According to this theory, when atoms bond, their atomic orbitals combine to form new orbitals known as molecular orbitals. These orbitals can be bonding, anti-bonding, or non-bonding, depending on how the atomic orbitals overlap. The bonding molecular orbitals lead to the formation of a stable bond, while anti-bonding orbitals, if populated with electrons, can weaken or break the bond. Molecular orbital theory provides a more detailed and accurate explanation of bonding, especially for more complex molecules. The valence bond theory is another important model in understanding chemical bonding. This theory explains bonding as the overlap of atomic orbitals from two atoms. When atomic orbitals overlap, electrons are shared and a bond is formed. The extent of the overlap determines the strength of the bond. For example, a single covalent bond results from the overlap of two orbitals, while a double bond results from the overlap of two sets of orbitals. Valence bond theory also explains the concept of hybridization, where atomic orbitals mix to form new orbitals with different shapes, allowing atoms to form bonds in specific geometric arrangements. In modern chemistry, the theory of chemical bonding is fundamental to understanding the properties and behavior of molecules. The development of computational chemistry and molecular modeling has further expanded our ability to predict the structure, reactivity, and properties of molecules based on their chemical bonds. Researchers use these models to design new materials, drugs, and chemical processes that have a wide range of applications, from renewable energy to medicine. In conclusion, the theory of chemical bonding is a critical framework that explains how atoms combine to form the molecules and compounds that make up the material world. Through ionic, covalent, and metallic bonding, atoms interact in specific ways to achieve stability. Over time, advancements in our understanding of atomic structure, molecular orbitals, and the nature of electron interactions have enhanced our ability to explain and predict chemical behavior. The theory of chemical bonding is not only essential to the study of chemistry, but also to the development of new technologies and solutions for a variety of challenges facing society today.